So we've seen in previous video that the potential is a bit like an electrical pressure, and the potential difference between 2 points is what gives rise to current flow. So it's explained by this equation here, which is called Ohm's law, and it basically tells us that for a given resistance, if as long as the resistance stays the same, then the current through a component is proportional to the potential difference across a component. Notice the use of the words through and across. Okay. Now, what that basically means is if we make a circuit, and I'm going to do a cell like that. I'm going to be very careful, and I'm going to pick myself a component called an ohmic resistor, which is basically just a resistor that has constant resistance. And I'm going to introduce this new symbol to you, which you might not have seen before. And that just means it's a variable potential supply. So it's just basically a power pack. I can change up the power, change up the potential difference. So if I was to set this circuit up with a resistor, then I would find that as I increase the potential difference V, then as I do so, the current will go up. And as I change if I then change the terminals around and made the potential difference drive the current in the opposite direction, as I increase the potential difference in the opposite direction, I'd increase the current in the opposite direction. And so this is the standard VI graph for an ohmic resistor. Okay. Now this should be GCSE revision or GCSE knowledge. Of course, there are other components that we need to know about. So if we change this now, so that's for an ohmic resistor. If we now take a little gander at what would this look like if I change this and put a lamp in there instead, just a normal filament lamp. Well, when it's cold, when it's just a very small potential difference, we get a very small current. And so for the first bit, we're going to get a graph that looks like that, straight line, i.e. Ohm's law is obeyed for a small section. But as it gets hotter, as current starts running around it, what happens is the electrons start colliding with the nuclei of the atoms and with each other, and they start to create heat, and that excites the whole system and gets all those nuclei jubbling around, and because of that it's harder for the current to flow through. And so with increasing potential difference, we don't get a uniform increase in current, so it sort of tapers off like that. And we do a graph or something like that. Now this should be the same as this, but in reverse. Okay, so this would be for a filament lamp. Okie dokie. So that's the second component that you need to know the VI graph for, filament lamp. And the third and final one is a diode, a semiconductor diode. Now, a semiconductor diode is basically like a one-way valve. So the symbol for it is an arrow, like that. Now remember, conventional current goes from in a circuit diagram. This cell symbol, the long stick is the positive terminal, and the short stick is the negative terminal. And even though electrons are going that way, conventional current, we say, is going the opposite way. Now, we won't go into why that is here in this video, but conventional current goes from positive to negative, and this arrow means it can only go through in the direction of the arrow. So this is set up right. Now, in this situation, as long as the potential difference is in what we call a forward bias, then as we increase the potential, it will go up in a uniform manner. When we put the potential in the reverse bias, then basically we don't get any current going through. Well, we do. We get a tiny little leak. So it just runs through, and that's just below the axis there. Now, if we're going to be really pedantic about it, actually, there's a small switching on current. You don't get anything until you get to there's a little step like that. So there's a very tiny voltage that steps it up, and that's really useful in transistors. But I think that's maybe going too far. You just need to know that really, as the potential difference increases, the current increases. It's uniform in the positive bias, and in reverse, there's nothing. Now, like I say, when I say nothing, there's not quite nothing. There's a tiny little leak that can go through, but it's very near to nothing, so it's hard to represent it. And so this thing we call a semiconductor diode. Diodes are these things here. They're just one-way switches, one-way switches. Now, of course, the classic thing that you probably use all the time or see all the time is an LED, which is a light emitting diode. And to make it an LED, we just put a circle around it and put some little waves coming out of it, and that's the symbol for LED. Both LEDs and non-LED light emitting diodes, as well as non-light emitting diodes, all show the same pattern on the VI graph. So those are the three things that you need to know about: the ohmic conductor, which follows obeys Ohm's law; the filament lamp, which obeys Ohm's law for a little bit but then stops obeying it; and the semiconductor diode that obeys Ohm's law in the forward bias but not in the reverse bias.